In today's video, Mike Wazowski is kicking us off because you may have seen this giant symbol in Monsters University. One of the fraternities that they face in the scare games is, the Eek fraternity, right? Is Slugma Slugma Kappa. That Slugma symbol that maybe you saw in Monsters University. That Slugma, which is their joke in the movie, is the monsterified version of Sigma, right? This is Sigma, this symbol right here. So that's the actual name of that symbol is Sigma. And what Sigma notation does in mathematics is it represents a summation. Summation meaning we're adding quantities together, right? And we have a very precise notation for this. The sigma itself means that we're performing addition, right? You could almost think of it as S for sum, right? For taking a sum. What are we? So that's the name of the S, right? This giant symbol is called the sigma, right? This is called sigma. And then what are we adding? Well, we're adding this right here. We are adding this is called the summand. So that's what this a sub n represents, right? This is called the summand. And that a sub n, it's a sequence of quantities. You can also think of it just as a function of n, right? Think of it as some expression perhaps involving n, and it's going to be a numerical expression that we can add to other numerical expressions. But formally, that gets called the summand, right? The thing that's being added. So that's our a sub n, right? Then we have a couple more really important pieces of notation here. One of them is the index. So this number right there, which also appears as the subscript in the summand, right? That's called the index. And that is a symbol that really only exists inside this sigma. If you had some expression out here, that n is going to have no meaning, especially if you write it with a highlighter. If this n, out here would have no meaning whatsoever, right? The scope of that n is really only inside this sigma. So it's just a variable that the sigma uses in order to generate these quantities that are being added. So that gets called the index, right, is n. Then we also have over here, we have L, right? And L is called the starting index. So that's this symbol right there is the starting index. And because it tells you what value your index n starts at. So the very first term is going to be generated by setting n equal to L. That's how you get the first quantity that you're adding up. And it goes until M, and M, perhaps not entirely surprisingly, is then called the stopping index. So that's what's happening up here. This is the stopping index because you stop when little n gets to M, right? So whenever little n hits that stopping index, M, then you stop adding terms. Now, how do we get from L to M? Well, what you do, this is a unwritten assumption, an unwritten rule of sigma notation. What you do is you always count upwards by one, exactly one each time, from L to M. So we'll go from L to L plus 1 to L plus 2. Then you sneeze, then you do L plus 3, and so on until you get to M, and that's when you're stopping index. That's what your stopping index is. Tells you when to stop adding terms. So if we unpack all of this in general, what do we see? This is another way to say this if you want to write it in what's called expanded form, right? So this is, you could have a summation in sigma notation, but I could write out that very same summation in expanded form. I'm going to write a sub L plus a sub L plus 1 plus a sub L plus 2 and so on, up until we hit a sub M. That's so this is called, once again, said it in words, but just to write it, this is called the sigma notation for a sum. And this is called expanded form of a sum. Right? So that's what we're that's what we're witnessing here, right? Two different ways to represent the same thing. Let's look at this now in an example, right? This is a lot of symbols and formal notation. Let's look at it in a very specific example. Let's evaluate, right? Let's find what number it equals. So let's evaluate a summation. Let's evaluate the sum as n equals, let's say, 3 to 6 of n squared, right? So what do I have here? Just to identify all the parts of this. In this case, my summand is n squared, right? My index that I'm using is n, right? My starting index is 3. My stopping index is 6. Just to, we had some vocabulary up above, just to identify all of those parts. Now, how am I going to evaluate this? I'm going to evaluate it by just converting to expanded form, seeing what all the numbers are, and adding them up. So let's now say, if you want, you can say, how does one get from 3 to 6, right? Well, one at a time. That's always the answer to that question, right? So one at a time. So we're going to use, specifically, we're going to use n equals 3, then 4, then 5, then 6. So we'll have exactly 4 terms in this sum, 1 for each n value. So let's now expand this up. So let's take our summation, sigma n squared, n equals 3 to 6. And let's write this in expanded form. So I'm going to write 3 squared plus 4 squared plus 5 squared plus 6 squared, right? And notice here what I'm doing is I'm each of these terms corresponds to an n value. So I took n equals 3 and I plugged it into the summand. I took n equals 4 and I plugged it into the summand, right? I took n equals 5 and I plugged it into the summand. I took n equals 6 and I plugged it into the summand, and then I stopped because I hit the stopping index, right? How do I know to put plus in between? Well, that's what the sigma tells you to do. The sigma is telling you to add all of those quantities. So now from here, I can just do the arithmetic, right? I can say, okay, this is 9 plus 16 plus 25 plus 36. And now we can just do the arithmetic, right? We can grind out the arithmetic. So what would I have here? I have 9 plus 16 equals 25. Right? And 25 and 25 is 50, and 36 gives me 86. So there's my result. All right, there's the sum of all the numbers from all the perfect squares from 3 squared to 6 squared. Right? So there's an example of evaluating sum by just unpacking it, right? Expanding it out, seeing what all the terms are, and adding them up. Okay. So next, what I want to look at is, now that we've done an example, I want to look at some properties of summations. So let's look at a property. So properties of summations. And in particular, let's look at, this is a very nice one. Let's look at this. If you sum from n equals, say you sum from n equals 1 starting index to another, right? And then you sum from m plus 1 up to another stopping index. So let's say LMNOP. We're up in that part of the alphabet, but I don't want to use O because it looks like 0. Right? So say we have this, right? What would this equal? Well, this would equal what? Imagine it in expanded form. Here, I would have a sub L plus a sub L plus 1 plus a sub L plus 2 plus all the way up to a sub M, right? That's that first summation in expanded form. So I took this and I expanded it. Now, what could I add to that? I could add to that this second expression. What is this? This is also a summation, right? this is a sub m plus 1 plus a sub m plus 2, and so on, and we keep going until we hit a sub p, the other stopping index, right? Now, what would let's think about what happened here. I went from a sub l to a sub m, added up all of those terms, and then I had a sub m plus 1 in the new summation, and a sub m plus 2, and so on all the way up to a sub p. Well, that's the same as if I just erase those parentheses, it's the same as if I hadn't ever really stopped here and I hadn't restarted here, right? That was sort of unnecessary. Instead, I could just say this is one gigantic sum. Add up all the numbers from L to P of a sub n, right? So this is an example of a way that sometimes you can clean up summations. If you see two summations, and right, sometimes you can maybe resolve it into just a single summation. Not all the time, certainly not all the time, but sometimes you can, right? So there's a nice example of an identity on summations, right? So this here's an example that we could do of this that would be a little more concrete. You could say, for example, suppose I had the summation of n equals, let's say 1, 2, 2 of n squared plus the summation of 3 n equals 3 to 6 of n squared. Say I had that. Well, so this is the old sum that we just worked with, right, in our previous example, but I added another little sum to it over here. Well, what is this? This, to again kind of illustrate that proof from up above, this is 1 squared plus 2 squared. That's coming from the first summation. Then this one is 3 squared plus 4 squared plus 5 squared plus 6 squared. Well, essentially, it was unnecessary to express that as two different summations. Instead, we could just say this is all one gigantic summation, starting at 1 and ending at 6 of n squared. Right? So there's a example of combining two sums into a simpler expression involving just one sum. Now, here's, because of that, you could also do it the other way, right? If you have a summation and you subtract a summation from that summation, right? You can say, what's happening here? The first two terms are canceling, but the rest live, right? So the difference of those two summations gives me my original summation from this example up here, right? So that's, you could express that summation as the difference of two other summations. All right. Now, you might say, well, who cares, right? That I could express this summation as a difference of two other summations. Well, there are some really nice formulas out there for evaluating summations. And certainly not every summation has a formula that goes with it, but many do, many do. And in particular, there is actually a formula for the sum of consecutive perfect squares. So if you have, and this is not something I'm about to prove or about to explain why this is true. Here I'm just stating it. Which typically, say in a pre-calculus course, in a calculus 1 course, usually this formula just gets stated and not proved. You might prove it in, say, discrete mathematics or an intro to proof course, maybe a differential equations course, but typically not in a, maybe even a calc 2 course, but maybe typically not in a pre-calc or calc 1 course. But so here, I'm just going to state it, the sum of consecutive squares formula. This says that if you add up all of the squares starting at 1, right, and stopping at some index capital N, what you get is this. You get a nice tidy formula. N times N plus 1 times N, 2N plus 1 over 6. This, at first glance, might look a little bit more messy, right? But now we have like this cubic polynomial. Oh dear, right? But in truth, it's not. Especially if big N is large, right? That's actually something a lot simpler, because here there are a lot of separate operations happening here. right? And as the stopping index grows, the number of operations will grow as well in expanded form, right? If you try to evaluate this sigma directly. Whereas on the right-hand side, this formula n times n plus 1 times 2n plus 1 over 6, no matter how large big N gets, it always takes the same number of operations to evaluate that formula, right? So this is, in most contexts, it's much preferable to have this evaluated as this nice, tidy little closed formula, as opposed to having it expanded out as a summation. So let's show how we could do this problem again. I'm going to evaluate exactly the same summation, right? The one we were given up here, but I'm not going to expand it out. Instead, I'm going to use these identities and properties that we mentioned here to evaluate it instead. So let's evaluate, right, this summation, sigma of n squared, as n goes from 3 to 6. Let's evaluate this again, but using the summation properties and formulas, right? Instead of just expanding it out, right, and doing the arithmetic. So we're not going to expand it. So here's what we can do. We can take this summation, right, sigma n squared, n equals 3 to 6. And just like we did up here, I could write it as the difference of two other summations. Why is this important? Well, because these both start at 1, right? And this formula down here starts at 1, right? This demands a starting index at 1. So that's why it helps me to take this and rewrite it as a difference of two summations that both start at 1. And then what I can do is I can take each of these and I can apply this formula, the sum of consecutive squares formula, right? Let's do the sum of squares with big N equal to 6, right? I'm going to do that on this first summation. And then here, I'm going to do the sum of squares identity with big N equal to 2. Right? And yes, on this second one, that's totally gratuitous, right? Saying that it's it's really just 1 squared plus 2 squared, this second summation, right? So using this sum of squares formula on it is sort of the putting a thumbtack into the corkboard with using a sledgehammer, right? But just to show the tool, I just want to demonstrate the tool. So we're excited because we just bought a new hammer and we want to use it, even if we're just putting a grocery list on the corkboard. So so let's do this. So here I have my big N equals 6. So I'm going to do 6 times 6 plus 1 times 2 times 6 plus 1, right, over 6. So that is my first summation. And then I'm going to do the second summation where big N equals 2, which is going to be 2 times 2 plus 1 times 2 times 2 plus 1, right? And that's also going to be over 6. So on this first expression, the 6's cancel. I get 7 times 13, which is 70, and 21 is 91, right? On this second expression, the 2 times 3 cancels with the 6, and I just get 5. I take that difference, 91 minus 5 is 86, which by no coincidence matches up here are 86, right? So we got the same value either way. We got it in a very, very different way, right? Here we got it by expanding out all the terms, doing the arithmetic. Here we got it by using an identity, right? Using this identity about summation, and really using two identities actually, right? One that lets us sort of decompose a summation as sums or differences of another summation, and one identity for a formula for the sum of consecutive squares. So this is our example here where we where we calculated exactly the same summation in a very different way. Once again, what's the advantage to this is suppose that this stopping index was giant. Suppose there were a lot of terms in this sum. Then what we did here with the sum of squares formula doesn't get much harder. It's the same amount of steps, just with a larger number, as opposed to expanding it out gets really tedious, right? So this is where these formulas and properties for summations can be super useful. Great, thanks. Go Uzma Kava.